The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next presenter is Carlos Coronado, and he's the senior engineer at Bechtel Power. And the title of his presentation is Dynamic Earth Pressure, Myths, Realities, and Practical Ways for Design.
Good afternoon again. My name is Carlos Coronado, and today I will be talking about dynamic air pressures for the design of liquid containing structures. My experience is mostly from the design of nuclear structures, so maybe this will present a little bit of contrast with the commercial practice. The presentation is going to be divided in 4 main areas. Initially, a little bit of introduction of background of what are the soil pressures that we have to design for liquid container structures that are partially embedded or fully embedded. What is like the standard practice, and for a standard practice, I mean pretty much what is in ACI 353. And then a more detailed type of analysis, kind of like what is required for nuclear structures, where you actually have to go and do a fluid soil structure interaction analysis of the structure, and a case study of the nuclear structure design accounting for fluids and soil structure interaction. And hopefully we will go over all these topics. I think I had more slides than what I will be able to go through, but in terms of the introduction and background, this figure depicts the type of loads that are acting in a partially embedded structure. This structure is assumed to have some sort of liquid here inside, and under static conditions, pretty much in terms of lateral soil pressures, the pressure that is acting is the at-rest pressure, and I think that there is no really any controversy about that. That is what is happening. The ACI 350 actually allows you to use maybe the active soil pressure, but you then have to go into the process of proving that the walls are deflecting or are deforming enough to guarantee the use or to warrant the use of active soil pressure. Now, when we introduce seismic, then the things get a little bit more interesting. And if the structure is still not sliding, the at-rest soil pressure for static conditions will still be acting, but then an additional pressure due to seismic will start developing. And what there is not really much agreement is this additional pressure, this dynamic soil pressure, how to estimate that. There are different methodologies that I will be discussing, but there is the theoretical and there is the experimental results, and pretty much mostly they don't match. Now, if the same structure under seismic load, but the structure slides, then we will have in one side the active static soil pressure, then again some seismic increment, seismic soil pressure, and then in the resistance side, we will be developing some pressure that will be higher than the at-rest soil pressure. And for a sliding to happen, pretty much we could just calculate the equilibrium here and see if the mobilizing forces are larger than the resistant ones. So with this background, I'm going to try to go on the standard practice. We went over this exercise because in the case of nuclear structures, actually ACI 349, that is the code for designing of nuclear structures, this really doesn't provide a MASH guideline. And ASCE 4, which is also the standard for design and analysis of nuclear structure, doesn't really get much into details of how to analyze buried structures that has liquids inside. So when we were doing the design of one of our structures, we went and looked at 353, which is produced by this committee. And then what it says in chapter 8 is pretty much that the structure has to be designed for considering dynamic air pressures, but it doesn't really set or doesn't recommend a particular procedure to calculate those dynamic air pressures, although the assumption mostly is that you will be using Mononobe or Cabe or some method like that, which is like the most popular. And it also recommends that for static conditions, you have to use K sub 0 unless you can demonstrate that Ka can be used. The other thing is for calculating the base shear, it gives this equation where pretty much is assuming that these are fluid pressures, dynamic fluid pressures, and wall pressures, root forces, wall forces, and this is convective pressures from the liquid inside. It assumes that the impulses, the walls, and the root are kind of acting in phase, but that the seismic pressure, the lateral pressures due to soil, they are out of phase from these other guys. And actually, it's kind of consistent with some experimental results, so maybe it's not too far away. However, when you are designing a nuclear structure, normally the requirement is that you have to assume that all these forces are in phase, which is pretty conservative. Now, the code or the standard from this committee, in case of calculating the moments for design of the walls, it mentions that you should include any moments due to dynamic soil pressures, but it really doesn't provide, like in the case of shear, something here to say, okay, you should calculate that moment also as the SRSS or so on. But if we were to use this code, one way to do it is, first we need to know if we should be using addressed soil pressures or active soil pressures. So one way to do that is doing a stability and a sliding analysis of your structure and compare if the driving forces are larger than the resisting forces. In that case, if that's the situation, then the structure is sliding, and then you should be able of calculating using active pressures. If the structure is not sliding, then you should be using at-rest pressures. And then to calculate these very different terms that appear in here, the code does provide guidelines. Okay, you are going to do the stability analysis. You have to pick anyways where the different interfaces along which the structure could be sliding, and then you have to calculate the different forces acting on the structure, forces due to fluid, forces due to air pressures. So to calculate the forces due to fluid, the code does provide some guidelines and some simple formulas to obtain what will be the impulsive pressures due to the fluid, and then using that approach you can obtain the impulsive forces. For calculating the dynamic soil pressures, there is not really guideline, but one of the methods that is widely used is Mononobe or Cabe, although this method is in theory for calculating active seismic air pressures. There is a lot of discussion that is so conservative that actually you could use it even if the structure is really at rest, and then the equation, although may look a little bit complicated, it can be simplified And you could separate the component of the salt pressure due to a static condition from the one due to dynamic conditions, and that one due to dynamic conditions is normally proportional to 0.75, the equivalent lateral acceleration coefficient used for the design. Now you decide to use then that if you say that no, in reality the structure is not moving, I should be using the address. One simple way to calculate the address is to say that is twice the value of the active, and that is also widely used. Alternatively, for calculating seismic pressures address, we could use diagrams like this one, where are based basically in research done by Wood in 1973, and this will give us very high seismic soil pressures, extremely high, that actually don't correspond with experimental results. However, for a nuclear power plant or for the design of nuclear structures, this is what we normally end using all the time. And here is a simple calculation of how those different soil pressures finally can be obtained. In parentheses is if you were calculating active pressures, this is active static pressures, sorry, in parentheses is the at-rest pressure, and without parentheses is the active case. So obviously the active is always lower than the at-rest soil pressure. The same thing for the dynamic case, and notice here that is practically practitioners, engineers, normally they consider that the dynamic soil pressure follows a distribution that is kind of inverted from the static one. And this is after, in the 70s, Sid and Whitman, they said that the dynamic soil pressure distribution should be acting not at 1/3 from the bottom, but at 1/3 from the top. And that's actually also the same recommendation that this committee has. However, experimental results are against this, but this is what we use in practice. Okay, if you had water also in your backfield, then you have to consider also that as one of the driving forces. But if your backfield is well drained, then really it's just the hydrostatic pressure which will be acting all around the structure, so it won't really produce any driving forces. But if the backfield is not well drained, then Whitman said that sometimes due to the shaking of the ground, the water pressures could increase up to 35% from the hydrostatic. So pretty much once, let's say if you are following like the standard practice, once you obtain the different forces, let's say that you started assuming that your structure is not moving, you go had the different forces, applied equilibrium to your structure, and then if the resistance forces here at the base and on the sides and here in the back are larger than the driving forces, then pretty much you are done with the analysis. If these driving forces are larger, then pretty much you will have to redo the analysis, assuming now that you had active conditions, and then design for that. So that will be like kind of like the standard practice. Now, I would like to show very briefly some experimental results. These were done in University of Davis in 2007, and these were used during the design of the bar extension in San Francisco. And quite interesting results were obtained in there using centrifuge models, two different retaining structures were tested, one that is rigid, one that is very flexible, or one that is flexible. And I won't go much into the details, but here are some results. This dot figure shows just the static pressure distribution before applying any checking to the model, and they are kind of well predicted, especially if you check the model first and then go and measure after the checking what is the distribution of soil pressures. They kind of were well predicted by theory. Now, they went and measured what was the maximum moment at the base of these retaining structures, and the points are the data from their measurements, and these outliners here are the results obtained if you use mononove or cave, which is for active conditions, which anyways it shows that is a conservative approach for the different earthquake motions that they consider in this experiment. And in terms of pressure distributions, again the same situation. Normally mononove or cave was enveloping, so pretty much if we design using mononove or cave is already conservative. If we use now the elastic pressure distributions from wood, it will be even more conservative. But anyways, now I will show you what we do for nuclear, which is even more conservative. So in this case, in the structure has liquid in there, we can go and model the fluid structure interaction using fluid elements, or we could just create a simplified model where the interaction of fluid and structure is accounted using just lump masses. Based on, let's say, ACI 350, we could calculate what lump masses to use. In terms of the soil structure interaction, then we normally use a specialized software for doing this, typically a computer code called SSI, and that software uses structuring modeling techniques to account for the soil structure interaction. And this is just a sketch depicting like the different steps that software goes into to create the model of the structure and the soil. But I won't go into much details. I will just go now into what we did for, this is an intake pump station for a nuclear power plant. This structure is critical just for the main purpose of this structure is that if you had an accident, then the pumps in this structure should be functional after the maximum seismic event, which is called safe shutdown earthquake. So we have to design this structure to be functional because it's the one that is going to be providing the cooling water for the reactors after a design event. So we created a finite element model of the structure in order to model the fluid structure interaction effects. Rather than using fluid elements, we use a simplified model, and I will show that simplified approach was matching quite okay with a more detailed analysis. And some of the reasons for this is that the software that is used for soil structure interaction analysis doesn't have the capabilities of actually accounting for fluid structure interaction. In here, different seismic environments are considered, and also different soil profiles with upper bound, lower bound, and best estimates of the soil properties. And for design, we use directly the results from this analysis at the moment of designing the walls. So we really didn't go into calculating dynamic soil pressures. this because they were coming directly from the analysis. This is a sketch of the model, just hollow. The model was done due to symmetry. This is one of the portions that has water. Some studies were done comparing the simplified methods of the analysis of fluid structure interaction versus detailed fluid structure interaction modeling. Here it cannot be seen very clearly, but dotted lines are simplified. Solid lines are the more detailed analysis, and the differences were not significant. So we went with the simplified approach. This is the soil structure interaction model, and these are like the different soil profiles, the properties of the soil, starting from top to bottom, and considering lower bound, upper bound, and best estimate soil properties, and the different earthquakes, ground motions that were considered. And as a result of this, we get different moments and membrane forces in the structure and conduct the design using simple spreadsheets. Like for instance, we will get results at different locations and use those for design. My opinion is that what we are doing in nuclear is very conservative, but given the importance of the structures, is definitely deemed necessary. And now I guess I'm ready for the conclusions. So pretty much in this presentation, I provided like the two views, how you could design a structure, a liquid container structure using simplified approaches, or one using a more detailed soil structure interaction analysis, but that is kind of almost not possible for the typical commercial structures that we deal with on a day-to-day basis. And I think that the codes should be provide more guidelines about what air pressures to use, not just to say that they should be considered. So,
Thank you. Maybe just one or two short questions.
For the checking of sliding stability, what's the recommendation you will use, and what factor of safety you check against?
yeah, in there, when we were checking, we were just verifying if the factor of safety is less than 1, then it means that is a sliding. And then because this was under seismic conditions, so all, at least for a nuclear structure, all the factors are just 1 because it's the maximum choke down earthquake. So all the load factors were 1, and the safety factor against a sliding, it was less than 1. That was meaning that the structure is a sliding, and then we consider the KA conditions.
So was it based on a level load like 160 and 170? That's what using SCE.
Sorry, can you?
Oh, I'm asking the low combinations that are based on the data load and seismic load.
Yeah, the low combinations were based on ACI 349 because I was dealing with a nuclear structure, but if we are dealing with a typical liquid container structure, I guess you would have to use the low combinations in ACI 350.
Okay, so as you said earlier, factor safety is based on 1.0, not higher than 1.5.
Yeah, just to verify the thing is a sliding, because of course, we need to guarantee that at the end of the safety factor, at least for nuclear structures under this very high seismic force, what they require is that it has to be larger than 1.1. But, okay.
Thank you, guys. Thank you.